Okay, let's keep going. Okay. Now, since current is flowing through the circuit, yeah, and it takes time, so as you know, yeah, current times time gives you the charge. Okay, current measures the rate of reaction. This is very important. Okay, the electrochemical reaction, okay, the rate is simply current. Okay, when you measure current, that means that uh, that is the electrochemical reaction rate. Okay, so it is very easy in electrochemistry to measure the reaction rate. Okay, and then this relation is really important. Charge, symbol is Q. Charge equals current times this time in second. Okay, moles of electron is what? If you divide this coulombs, okay, charge by the the coulombs per mole, okay, is n. This one Q divided by F. F is what? This is Faraday constant. All right. Faraday constant is the by definition is the charge of 1 mole electrons. Okay. So if you divide the total coulombs by Faraday constant, that will be number of electrons. Not number of electrons. The number of moles of electrons. Okay. So relation of moles to let me see. This is the Faraday constant. Okay. This is very important. Okay, and if for the chemical reaction doesn't if have one electron, and then this is one, and if it has n electrons, and then you have to divide this it divided by nf. Okay, and then here is the let's look at this example. uh, Let me see. The question is, if a current of 0.17 ampere flows for 16 minutes through a cell, how many grams of copper will be deposited? Okay. First thing, what you have to do is to calculate the total charge. Okay. So this is current, and this is time, and then you convert into second. Okay. So 0.17 multiplied by 16 times and 60. Okay, this is a charge, and then you divide by a Faraday constant. Okay, and then you get 1.7 times 10 to minus 3 mole for electrons. This is moles of electrons. Okay, but kappa, you see, uh, to uh, deposit, kappa metal, how many electrons are needed? Kappa, divalent kappa, needs 2 electrons. Okay, so n is 2. To calculate the number of moles of kappa, you have to divide this number of electrons by 2. Okay, this is number of moles of kappa. Okay, and then the question is how many grams? So 1 mole kappa, is what you multiply by the kappa atomic weight, which is 63 times 0.546, and then you get 0.045 gram. This is the mass of kappa you expect. Okay, not difficult, right? And remind here, the cell potential here is E plus. Before, yeah, we use this symbol, but now in our uh, example, this is a cathode. Okay, and E minus, and in galvanic cell, Er minus El. R is the what? This is cathode in carbonic cell, and El is the anode, uh, represents anode. Okay, okay. Here, reduction always takes place at cathode. So this is the definition of cathode. Okay, oxidation always takes place at anode. Yeah, this is also definition of anode. Okay, yeah. And voltage changes when current flows. Yeah? Now it is important to know how, why voltage changes when current flows. Yeah, current flows means what? Hmm? As I said, current is the reaction rate in electrochemical cell. So current flows, that is what. That means that uh, reactions are, reactions keep uh, going on. Okay, Hmm? That's what current flows mean. Okay, in electrolysis, we always need a power supply. Okay, electrolysis. This is not a spontaneous reaction. Okay, since uh, yeah, when you are confused, think about the water electrolysis. Okay, Mm, even though you put two electrodes into water, the water cannot be split into oxygen and hydrogen gas, but you have to apply electrochemical energy, yeah, electrical energy into that system. So electrolysis, you always need power supply, yeah, to supply electrical energy. Okay, so equation is what? E equals this one. Okay, this is called open circuit voltage. Why? In open circuit voltage, no current flows. Okay, yeah. And then for each electrode, for cathode and anode, you apply Nernst equations. Okay, to cathode and anode. So here, let's go back to the original setup here. Yeah. This is cathode, this is anode. Cathode is the copper ion reduction, and an anode is water oxidation. Okay, let's write Nernst equations for uh, both electrode here, and this is for cathode. Yeah, copper, divalent copper, accept two electrons to become copper metal, and then E0 value is 0.339. And then since number of electrons is 2, okay, 0.05916 over 2 multiplied by log of this one. Okay, copper ion concentration is in the denominator. Okay, and then water oxidation is what? Yeah, so if you look up the index, let me see, not index, what's that? In the back, of your textbook, you find the the tables, yeah, and then you will see the oxygen reduction to water molecule, and then you find that the E0 value uh, is 1.229 volt. Okay, and then you know if we take two electrons, and then the 1/2 oxygen gas and hydrogen concentration are squared. Okay, this is the nearest equation for the anode reaction. All right, and then now we you well, the substitute necessary constant into these variables. Okay, for example, in this case, in this example, let me see, in your textbook, initial copper ion concentration is 0.2 molar. Okay, and then the oxygen gas pressure is 1 bar, and it's done in 1 molar proton concentration. Okay, so you substitute the necessary the values, and then you get this one. Well, this part is 0.318 volt, and this part is quite positive, 1.229 volt. And then since you have to subtract, then you get finally minus 0.911 volt. Okay, this one, and this is a negative sign. Okay, negative sign indicates that above this reaction, Ford reaction, is not spontaneous. Why? Because the calculated this voltage is it has a negative sign. So Gibbs free energy change is plus. So it is not a spontaneous, non-spontaneous reaction. So in order to drive this reaction, you take the power supply and connect this negative terminal to this copper plate and positive terminal to this platinum wire, and then you increase this voltage, and then you have to increase up to 0.911 volt, and then if you increase more, and then at that time, then the currents begin to flow. Okay, current begin to flow. Here, let me explain once again. When you put this negative terminal to this electrode, this negative terminal means that uh, the electrons are coming out of this negative terminal here, right? And then electrons are directed to this copper on the metal. So at the interface, the electrons are used to reduce this copper ion. Okay. In the meantime, these electrons are supplied from the water oxidation here. Okay. So this is electron flow direction. Okay. And current flow direction, current always comes from this positive terminal. This current flows like that. Okay, don't be confused. Okay, and then let's learn a little bit intriguing concepts of overpotential. Okay, overpotential in Korean 과전위. Over means overflow. Okay, too much. Overpotential is the voltage required to overcome the activation energy for a reaction at an electrode. Okay, this overpotential concept in electrochemistry is equivalent to activation energy concept in general chemistry. Okay, uh, let me ask you: do you think oxygen gas and hydrogen gas reaction to water spontaneous or not? What do you think? Hmm? Oxygen molecule and hydrogen molecule now react together at room temperature, okay? And then it gives rise to water molecule, okay, spontaneously. What is your answer? Hmm? The answer is yes, okay? That reaction is spontaneous. That reaction has quite a negative Gibbs free energy change, okay? But actually, you don't see, although you wait for your lifetime, you don't see that reaction takes place. Why? Why? Because oxygen and hydrogen reaction has very very high activation energy. Okay? In order to in order for the reaction to proceed is what? To overcome the activation energy. Okay, now in electrochemical electrochemistry, that activation energy is called overpotential. Here, let's look at this one. Now we are dealing with electrons. Okay. Hmm? In electrochemistry, definition, yeah, we can define electrochemistry in various ways, but my definition of electrochemistry is the uh, is a science of dealing with electrons. Okay, dealing with electrons. Okay? For example, here is the electrode. Okay, now electrode can provide electrons to species in solution, or electrode can accept electrons from the solution. Okay, some species in solution. Okay, let's assume that these electrons must go to hmm, this for example, this water molecule here, actually proton, hydrogen ion. Yeah, how do you do that? It should overcome this much of energy. This is called overpotential. Okay, overpotential. How do you uh, overcome this overpotential? You have to change the electrode potential. Okay, now let's imagine that. Now you increase electrode potential to change this electron this potential, and then if you gives more and more negative potential, if you drive electrode potential more and more negatively, and then this one, this energy level moves upward, okay, here, and at this point, and then although there is a small activation energy, and this energy is small enough for the these electrons can overcome this energy, and then electrons can go to this hydrogen ion, okay, for reduction. Understand? Yeah. So like in general chemistry, the electrochemical reactions also, electrons must overcome the some kind of energy called overpotential, for the reaction to take place. All right, and then in chemistry, how do you reduce or how do you overcome this activation energy? Usually you increase temperature, okay, reaction temperature. So when you increase reaction temperature by 10 degrees C, and then generally reaction rate increases by 2 times, okay. But in electrochemistry, okay, how do you overcome this activation, this overpotential? By changing the electrode potential. Very simple, okay. Okay, now applying greater overpotential, that means sustains a higher current density. Okay, let's look at well, let me see. Here, yeah, this example is the overpotential for the liberation of hydrogen gas at the kappa surface here. Okay, let's look at this table. This table tests the overpotential for gas evolution at various current densities at 285 58 degrees C, and I, I'm sorry, this is may be wrong. This is 25 degrees C. Anyway, um, the point here is that this there are a lot of different electrodes here, okay, and the question is how much potential you have to apply to produce hydrogen gas or oxygen gas at different this materials, okay. Here is for the kappa case, kappa electrode, yeah, you have to increase this one uh, for this potential, yeah, potential depends on the current density. If current density is simply 10 ampere per square meter, you need 0.479 volt. But if you increase the current density to 10,000 ampere, and then you have to increase the potential to 1.254 volt, okay. Yeah. Hydrogen and oxygen evolution reactions are mostly most widely studied electrochemical reactions, okay. And the for the let's take this example, platinized platinum, right? This is not smooth platinum, very, the surface very rough on the surface is called platinized platinum, okay. And hydrogen gas is very easily produced because this overpotential is quite small, okay, quite small. Large overpotential means that you have to additionally, apply the potential, okay. But if potential is zero, which means that the electrochemical reactions take place at a theoretical value, okay. So hydrogen evolution at platinum electrode is quite easy because this overpotential is quite small. But oxygen evolution is difficult. Yeah, much difficult because here is at least about zero point 0.4 volt. You have to 0.4 volts uh, applied more, okay, to what oxidized water, okay, and at silver electrode, hmm, hydrogen evolution is not easy because this much of potential is required, okay, and gold electrode potential of hydrogen evolution is small, and graphite is very high, and let's see, the mercury electrode hydrogen evolution is quite high, or potential is quite large, okay, like that. And as the current density increases, or potential also increases, okay. You see, you take a look at these values, okay. Yeah, so potential concept is very important, you know. So the our reality is quite different from theory. From theory, yeah, you can calculate this like that, this one, this that means the minus 0.911 volt is enough to produce to deposit copper and produce oxygen gas, but actually you have to increase more. In other words, you have to drive uh, more negatively, yeah, uh, to deposit copper metal and to produce oxygen gas, okay. So low over potential means that that reaction, very smoothly, very easily takes place, okay. Large over potential means that you have to add more electrical energy, okay. Yeah, that's the difference.